Hello, everyone. I hope we're properly live now. So our next speaker is Titouan Carette, who's going to tell us about the SZX calculus,
SZX, yeah.
and scalable graphical quantum reasoning. Go ahead, Titouan.
Thank you. So, hi everyone, so I'm Titouan Carette, and this is joint work with Dominique Horstman and Simon Perdry, and I'm here to introduce you an extension of the SZX-calculus, SZX-calculus, S for scalable, which is designed to handle registers of qubits. So I will use a running example. I will speak about graph state. The idea of a graph state is that you have a graph and you want to construct a quantum state corresponding to its graph. So how you do this? For each vertex, you take a ket plus state, which is a green node in ZX. And for each edge, you will apply a control Z gates like this. And then using spider rule, spider fusion, then you see you have a state which is very close to your original graph. So this is what a graph state looks like in a ZX calculus. And graph states enjoy an invariant.
Are you still there, Titouan? You seem to have frozen for me. I'm not actually getting any sound from you, Titouan.
Show you something like this. So here you see we have a graph state, we have a vertex U, we have its neighborhood. And if I want to do the proof again, what I do, I apply my phases, and again, I copy the red, then Hadamard gate, then slide, and it cancels. So this is a.
Titouan, could you backtrack for a little bit, because you're having some sound issues for the last minute or so.
Okay.
We couldn't really hear you. Also, you've got a bar at the bottom of your screen, which you might want to hide.
Oh, yes, right. That's right. Okay. So can you tell me where I was?
I think you started talking about the graph states and the CZ gates, and I think at some point after that, it disappeared.
Okay. So here we have CZ gates, CZ gates. Okay. If I put it this way, we apply them for each edge of the graph state. And then using spider fusion, we obtain diagrams which is very close to the original graph. And this is what a graph states look like in the ZX calculus. Now graph states, they enjoy an invariance property for some transformation. If I choose a vertex U and I apply on it a red pi gate, and on its neighbors, I apply a green pi gate, and what happened, you can see it here. The red is copied by the green, then the Hadamard gate change the color, then it slide, and they cancel. So a graph state is invariant by this kind of transformation, and in fact,
I didn't actually see that. Maybe your slides are frozen. Sorry.
Wow. No, on my side it's okay. Do you see something happening now?
Your slides have gone away completely.
Right. Good.
You need to share the screen again. You're not sharing it right now.
Okay. Wow.
It's not a proper virtual talk if there aren't some technical problems.
Are my slides back?
Yeah, now they're back. Thank you.
Good. Maybe I will be able to finish this talk. I don't know. Okay, so let's come back to my transformation. I applied this red pi. There is a copy rule. Then the Hadamard gate change the color. We have it slide, and they cancel. So graph states are invariant by this transformation. In fact, this is even an alternative definition of state. If you have a quantum state, which is invariant by this transformation, you know this is the graph states corresponding to your graph. So this is very clear with a specific example. When I give you a graph in ZX, you see this property is true. But if I want to do a general graphical proof that is valid for any graph, then I have to draw you something like this. So I have a graph state G, I have a vertex U, and I have its neighborhood. And then I will do my transformation.
I think your slides are frozen again, or at least we're still on slide 2.
Ha! Okay.
Titouan, maybe you can try turning off your video feeds, because maybe this is causing some of the problems. Can you please try that?
Okay, do you see my screen?
I still see the screen, it's still on slide 2.
Okay, so.
Okay, so now your screen is gone. Do you want to reshare that?
Yes. This. Hop, sharing. Okay.
Okay.
Okay, so let's try to go toward the slide 3. Okay. So I apply my transformation. So copy, Adama, slide, cancelled. And then I will try to do the same proof, but with a general setting for all graphs. So I have this. Does anyone see the slide 3? Did we manage to do this?
Yes, we're on slide 3 now.
Yes, good. Okay, so here we try to do a general proof. So I apply my transformation. Here again, copy, Hadamard, its slide, and they cancel each other. So now you're all convinced that this is true for any graph state of any form in SZX-calculus. But you are convinced because you were able to guess all the implicit data that are hidden by all those dots here. And this is not formal enough for a graphical proof assistant, for example. So this is a natural question to wonder how to get rid of those dots. And in fact, this is not a new question. A lot of PhDs that have been done on this subject by very clever PhD students. And for example, you can use bank boxes. You have a very nice theory of bank boxes to handle those dots. But here I will present you something different, not weaker or stronger, just kind of complementary. So what will we do to get rid of those dots? We will introduce new types. Usually in SZX-calculus, we just have one type of wires, which is the type corresponding to qubits, wire of size 1. And I will add some other wires, big wires of size bigger than 1. So wires of size n represent a register of n qubits. So this is not a prop anymore, but a colored prop, and the colored corresponds to different sizes. So notation, when I write k.n, this stands for k wires of size n. And with this, some little things we need to be careful about. First, if I have k times wires of size 0 or 0 wires of size 1, this is the same thing as 0 wire, and this is the tensor unit, the complex number. So this is not so surprising, but we must be careful that 2 wires of size 1 are different than 1 wire of size 2. These 2 different things. This is the whole point. But those 2 types are isomorphic. We will see we have an isomorphism between them. So if we have new types, now let's introduce new generators to construct them. So I have first divider. So it extracts just 1 qubit for a register of n plus 1 qubits. And we have the gatherer, which is able to take 1 register of n qubits, you add 1 qubits, and you increase the size of the register by 1. And those 2 generators, they satisfy 2 equations called the elimination and expansion equation. And in fact, you see those equations are exactly saying that those 2 things, dividers and gatherer, are isomorphism. They are inverse of each other. So I recover that 2 wires of size 1 is the same, is isomorphic to a wire of size 2. If you take just this, you have a colored graphical calculus, and a very simple one. This is a very simple colored proof because you have this Fouriering theorem stating that if you take 2 diagrams, if the types match, then the equation holds. So any well-formed, well-defined equation is true. And from this, you have a lot of consequences. First, you can define generalized dividers when you extract more than one qubit, and there is only one way to define this. In the same idea, you have this associativity light equation, which is well typed, so it's called. And then you can define n-ary divider and gatherer. In general, the things to remember here that as long as you count your qubits well, then you can do whatever you want with dividers and gatherers. They are very easy and intuitive to use. So now let's see how they interact with the generators of ZX to build SZX. So we have new generators, scale generators. For example, here you have a big Hadamard gate acting on n of a wire of size n. So what happens if this big Hadamard gate meets a divider? You see, in fact, that this big Hadamard gate is just n, the tensor product of n Hadamard gates, okay, on all the qubits of the register. So this is a little bit more tricky for spiders, huge spiders. So first, let's not care about the phases. We see if you have a spiders of size n, then this is in fact just n spiders acting respectively on the corresponding qubits in the register. And then, considering phases, in fact, we can do more than just applying n times the same spider with the same phases. Now, a spider of size n can carry a vector, a list of n phases, and then we just apply the phases respectively on the corresponding qubit. So here we have ht, the list of phase, h is the head, which is a phase, and t is the tail of the list, another list of phases. So now I've introduced new types, new generators, new equation, and a natural question I think you can ask is, what about the nice completeness result we used to have about ZX? Do we still have it? And the answer is yes. We just need to extend a little bit the interpretation. So now a diagram, we will interpret it as a linear map, but we also need to keep track of the type, of the organization of data, of the qubits. So for example, the identity on a register size n is just the identity on the Hilbert space, and you just send one wire of size n to one wire of size n. This is easy. For the Hadamard gate of size n, you see it's just the tensor product of n Hadamard gate, and you send a wire of size n to wires of size n. The interesting part is when we try to interpret the divider, because here we see the divider is doing nothing on the Hilbert space. This is the identity. But when you look at the type, you see take one wire of size n plus 1 and send it to one wire of size 1 and one wire of size n side by side. So I just give here the interpretation of the spider. It's the same things. So what is important to see here is that in fact, ZX and dividers and gatherer are orthogonal. They are not acting on the same thing. ZX is acting on the Hilbert space, and the dividers and gatherer are just acting on the organization of data. And you can understand it with this result. In fact, for each diagram of SZX, we have this normal form. It's always possible using the rule to rewrite it this way. First, you divide everything. So you end up with just wires of size 1. Then you apply usual generator of the SZX-calculus. And at the end, you gather everything as you want, as you need to. And from this normal form, you recover your completeness result. So there is no problem about completeness. Okay. So now let's see what is new in this calculus. What is interesting is that I can use dividers and gatherers to manipulate large graphical structure. So for example, if I take a bipartite graph between green nodes and red nodes, like this, so you see some scalars here, and as Neil said before, in fact, you can get rid of them. This is just because we were not clever enough to choose a good normalization. So I will not care about the scalar in this talk. They are just here for the sake of exactness. So then we have a bipartite graph, and this A here is a 0-1 matrix stating which green node is linked to which red node. So in fact, this is just the B adjacency matrix of the bipartite graph. And then using dividers and gatherer, we are able to box this, and this is what we call a matrix arrow indexed by a 0-1 matrix. So you see here, the 0-1 matrix is of size n times m, and not 2 to the n times 2 to the m. So in fact, here we have just a very compact way to represent this diagram. So why am I interested by those matrix arrows? First, because the interpretation is nice. Just nice. To auto-interpret this, you just apply the 0-1 matrix to the 0-1 vectors of the basis. Okay. Oh. In fact, you can give another definition of those matrix arrows. It's possible to define them inductively.
Titouan, your sound has just dropped out.
Arrows corresponding to the matrix product.
Titouan, we couldn't hear anything you said after these things are defined inductively.
Okay. So you hear me now?
Yeah, now you're back.
Good. So those things, I can define them inductively, and if I choose this definition, then the bipartite graph interpretation becomes a theorem. You can prove it from those axioms. Okay, now let's look like other things we can derive from those axioms. First, if you compose two matrix arrows, then this is just the matrix products in F2, the field with two elements. You can also copy them and erase them using the green spider. You can add them with this in this way.
Your slides be changing because we're still on the same one as like when your sound dropped out.
This is very terrible. Okay. Do you see something changing, or are you still blocked?
No, it's still the same.
Okay. And now? Good.
Yep.
Okay. Nice. Do you see a new slide here?
Yeah, that's working.
Hi.
Except now your sound's gone again. Titouan, can you hear me?
Yes, I can hear you. But do you?
Okay.
Okay.
Yeah, now I can hear you again.
And you see? Are you seeing slide 9?
Yeah, I'm seeing slide 9 with one diagram in the bottom right.
Yes, and it's changing right now, right?
No, it's not.
Ha! Maybe I should
Having
just,
either sound or image, not both.
maybe I should just record this talk and send it to you. Okay, let's try again. So now you're seeing my screen.
Yep.
So you're seeing.
Yeah.
Okay. And
yeah.
is it changing?
Now things are moving, and I can still hear you for now.
Good. So you can compose matrices. You can copy them and erase them with green dots. And you can also add them. This is the addition is F2, so 1 plus 1 is equal to 0. And we have this nice property. Let me talk a little more about this one. So here V is a 0, 1 vector. Okay. So you see the general phases we saw before. And when this generalized phase go through a matrix arrows, you just apply the A matrix to V and see the generalized phases you have at the end. Okay. Now, if a matrix arrow goes through a Hadamard gate, then you just change the direction of the arrow and you take the transpose. And using this equation, you can give color swapped version of the equation of the first row.
Your sound's gone again.
Okay, so now.
Okay, now you're back. Sorry, you said you can use the color swapped equation, and then after that your sound dropped out.
Okay, so now do you see my slides moving?
No, I think your slides are frozen as well.
This is almost
So someone in the Slack suggested that maybe if you don't make them full screen, they might not freeze. I guess that might be worth trying out.
I'm ready to try everything.
Yeah.
Everything. Okay, so let's go. So you see my screen?
Yeah. Okay, yeah. So yeah, maybe if you just want to try and keep going like this.
Yes, yes, yes. Okay. So let's go back to graph states finally. So this is a graph states. So it's not easy to see, it's not so obvious. So let's open the matrix arrow. So we see here the Hadamard goes through the divider, then change the color, and here we see this is a graph state. But in fact, any graph state can be put into this form. How do you do this? You just take gamma to be a triangular matrix, which is half of the adjacency matrix of G. And then you have a graph state corresponding to G. So you do not have to believe me on this. I will show it to you using the alternative definition. We will just check that this diagram is invariant by the transformation I mentioned before.
Now your sound has dropped out again. Titouan?
Am I transposed?
Okay, now you're back. Sorry, you said something about invariant and then your sound dropped out.
Okay, so I will check that this graph is invariant to convince you that this is if you take half of the adjacency matrix for gamma, then you have the correct graph state. So I will apply this. So here U is a 0, 1 vector.
Yeah, your slides are frozen again as well, sorry.
Yes. Do I continue?
I don't know whether yeah, I mean, this does seem to be getting a little frustrating. I don't know whether the hosts have any other ideas at this stage.
I don't know for the audience, but personally, yes, I begin to feel a little bit frustrated. Okay, so I will try another. Okay, this is the last time.
Yeah.
It's the last time. Do you see my slides?
Yes, I do. And
see them moving?
Yeah.
Yes, okay. So I apply this, U is a 0, 1 vector. This is 0 everywhere except on the wire corresponding to the vertex U. So I'm just sending a red pipe gate on the vertex U. By definition, gamma is half of the adjacency matrix. So the adjacency matrix is gamma plus gamma transposed. And then the neighborhood of U is just gamma plus gamma transposed applied to U. So here, the green generalized phase is just sending green pi gate to the neighborhood of U. So now let's compute. I copy the green, it goes through Hadamard, it goes backward through the matrix, so this is the transpose of gamma. Then those two generalized phases are not acting on the same wires because U is not in the neighborhood of U, so they commute. Now I can just use spider fusion, they cancel. I just need to take care of the remaining red pi. So it goes through the matrix in the right direction. So it takes gamma, it goes through the Hadamard gate, and then cancel, and it's done. So in fact, here I just give you the same general proof as I've done before, but without any dots. So I managed to get rid of the dots. Okay, so let's conclude this very long talk, sorry. So nothing in what I've said is in fact ZX dependent. Taking any prop, you can add dividers and gatherers, and you have a colored prop. And if you add a completeness result, using the extension of interpretation I gave, you still have your completeness result. In this generalized setting, what we have done with matrix arrows, in fact, is just finding a model of interacting Hopf algebras in the SZX-calculus. And we knew that interacting Hopf algebras were complete for those F2 matrices. Okay, so it's not surprising that we have all those nice matrix linear algebra rules. In general, when we have two languages which have nothing to do with each other, if you have some completeness result, it's always possible to use this completeness result to give compact representation of diagrams. So for example, if you think this way, you can think about the spiders as being just clever notation for correlation, and we know that correlation are complete for extraspatial Frobenius algebras. And finally, what I've done here is just adding more types which does, and the new generators are just here to put data structure into the X-calculus. And I did this just with a very simple data structure, but it's just registers of qubit, but I think we can do it with other more complex data structure, and this would worth to try. So this is the end. This is the end of this talk. If you have any question, you can ask them in Slack or email me if you are shy.
Okay, well, thank you very much.
This is the end. Merci beaucoup pour votre attention.
Let's all thank the speaker in the Slack. I will put in the first clap emoji if I can get Slack to work again. There we go. Yeah, so I think given the technical issues we had, maybe it'll be easier and quicker to just deal with the questions in the Slack rather than trying to do those live on this meeting. But yeah, thank you very much. Apologies to the audience for all the problems. I think we've established that WebEx doesn't work terribly well on Linux. And
at least we have proved this.
Yeah, let's continue this discussion on Slack and move on to the final talk in our session for now.
Thank you.
Right. Bye-bye.